SwayamPrabha. Digital India. Educated India.
So welcome to lecture number 42 of the Statistical Thermodynamic course. So in this particular thing, we have already said that the zero of energy, or the zero of energy is pretty critical, and we said the four ways, the four possibilities that we can calculate it. Let's write following Lorendau, the formulations defining zero of energy for a diatomic molecule. Okay, so the formulation, first we write the formulation, then the zero of energy, and then the internal molecular energy. All right. So the formulation T naught, which we already know what it is. So the zero of energy is the ground vibrational level. Ground vibrational energy in ground electronic state. Ground electronic state. Okay. Internal molecular energy therefore becomes T plus d omega E Fj. Then if it is Te, this is the minimum of the Morse potential. Okay, for ground electronic state. Okay, so the total energy will be now, this will be now E plus half omega E plus Fj. And then there are two more, which are kind of new. One is D naught, which is a ground electronic state. Ground electronic state of dissociated atoms. So this is T plus omega E plus Fj plus rather minus D naught. And then there is of course DE, which is ground electronic state of dissociated atoms. Okay, so this is Te plus D plus R plus Fj minus T. Okay, so the T naught, so there are varieties of options. The T naught option is most common and it is available in the Genoff tables and stuff like that. We also, for an assembly containing reactive mixture, D naught formulation is mandatory. Okay, so the D naught and DE are related. So DE equal to D naught plus half omega E. This is the relation. Okay, when employing a harmonic oscillator model, valid for harmonic oscillator model. Okay. Harmonic oscillator model. So this clearly indicates that ground state vibrational energy can be either included or excluded when you choose the zero of energy. When it is permissible, we must obviously not try to mix up the two different formulations when making thermodynamic calculations. In the most standard case is to use T naught formulation, which is there in the Genoff table, Appendix E. Appendix E, Genoff tables. Okay, all right. So that is what we can do. Okay, now let's go to the rotational node. So the rotational mode, the energy of the rotational mode, we have rotation divided by hc. This we have written countless number of times now. J into j plus 1 into dE, where the degeneracy is 2j plus 1. So the rotational partition function becomes z rotation, summing over all j, gj, exponential ej, that is j by kt, which now becomes, if you write it properly, j equal to 0 to infinity, 2j plus 1, exponential minus j into j plus 1 into theta r. Remember, this is the rotational temperature now. Yes, where the characteristic rotational temperature is theta r, and this is given as hc into be by k, which is equal to h square divided by 8 I square k ie, where ie is basically mu re square. Okay, so this is the moment of inertia. Okay, so for homonuclear diatomic, however, we have inadvertently overcounted the number of available quantum states by a factor of 2 because of the inherent indistinguishability of the nuclear pair. This complication derives from the symmetry requirements of the molecular wave function. So as a result, partition function is restricted to only odd or even values of the rotational quantum numbers. Okay, so the rotational partition function can be expressed more generally as, without going into too much of a detail, it's the same expression, similar type expression, but however we have a sigma now, j plus 1 exponential minus j plus 1 theta r by t, where it closes. Okay. Okay, so sigma is basically a symmetry factor, which takes on the value of unity for a heteronuclear and 2 for a homonuclear, is equal to 1 for heteronuclear, is equal to 2 for homonuclear. Okay, homonuclear diatomic. Okay, so typically theta r is less than t. Okay, so if you do a expansion of the rotational partition function, you get z rotation is equal to t by sigma theta r, 1 plus 1/3 theta r by t plus 1/5 theta r by t square plus 4 by 315 theta r by t cube. Now, if on the other hand, if theta r is much less than t, now this therefore can be converted to an integral, okay, and z rotation therefore will become t by sigma. Okay, so for nearly all diatomics, okay, theta r is of the order of about 2 Kelvin. Okay, so this expression is more or less suitable because this is much less than the temperature T. So for certain molecules, of course, like HCl or OH, this theta is of the order of 15. So in that case, you need to do this series. Okay? But for like 2 Kelvin, this is sufficient to calculate the rotational partition function. Now, for hydrogen, for example, theta r is 87.55. So you need to, need to do the full expansion. You need to integrate it, because then you need to go to this directly. Okay. So there are varieties of ways in which you can do this. Okay, so the condition, we can write some protocols. This is just to give some idea. Protocols for evaluation of Z rotation. Okay. So if theta by theta r is less than or equal to 3, then we use the parent equation, which is the full expansion. Okay. Which is the expression that we this particular equation, essentially use this. If on the other hand, 3 is less than d by theta r, which is less than or equal to 30, then we use this expression. Okay. Now, lastly, if it is d by theta r is greater than 30, then we use the last equation, which is T by sigma theta r. That will be your Z rotation. Okay, so there are varieties of ways in which you can do it. Okay, so the most common scenarios corresponds to this, because this is where most of the diatomics actually lies. So therefore, our 2 standard partial derivatives. So one is this, Z rotation divided by dt at constant. This becomes equal to 1. All right, the other one, which is d by dt square, ln Z rotation divided by dt and v. This becomes equal to 1 also. So therefore, as for the translational mode, we again replicate the classical results predicted by the pre-partition principle. So U by RT rotation is equal to H by RT rotation is equal to 1. Then, of course, your CV by R rotation is equal to CP by R rotation is equal to 1. Okay. And the rotational contribution of entropy, therefore, becomes S by R rotation is equal to 1 plus ln T by sigma theta r. Okay. So for heteronuclear diatomics containing atomic hydrogen, okay, the partition function can be similarly expressed as the form that we already predicted earlier. Okay. So this okay. Now for heteronuclear diatomics containing atomic hydrogen. Okay, this is E by theta r is therefore something like this, which requires that we use the expansion. That means Z rotation would be written as T by sigma theta r and some correction term. So this Z correction term is the rotational correction term, as we call it. Rotational correction, which is basically the expansion that we talked about. Okay, is 1/3 theta r by t plus 1 by 15th theta r by t square, so long and so forth. Okay, so we just evaluate the first two partial derivatives. Okay, this time, term by term. Okay, so for those cases, ln z rotation divided by dt at constant v, volume is 1 minus zrc, zrc. And the other one is this. Ln z rotation divided by dt constant v is given as 1 plus zrc double prime minus zrc prime by zrc minus zrc rc prime squared. Okay, where zrc prime is 1/3 theta r by t plus 2 by 15th theta r by t square, so on and so forth. zrc double prime is equal to 1/3 theta r by t plus 4 by 15th theta r by t square, so on and so forth. Okay, so we have the rotational contribution for internal energy, enthalpy, and specific heats would be U by RT. Rotation is equal to H by RT. Rotation is equal to 1 minus ZRC prime by ZRC. And similarly, CV or rotation, CP by R rotation is equal to 1 plus ZRC double prime minus ZRC prime divided by ZRC minus ZRC prime ZRC squared. So you can develop this for all the remaining thermodynamic properties, including entropy and a lot of other things. It's like some tedious calculations, but effectively it is the same way. So some of the unique features associated with the particle distribution over rotational energy levels can also be found. We can give this a study material. You can study the rest of the chapter where you can find out that what are some of the unique features of this rotational quantum numbers. So the rotational contribution, so we can just do a solve math. Rotational contribution to entropy, for example, to entropy for say HF at 300 Kelvin. Okay. So HF has got a rotational constant. This you can find it out in the tables. This has got a rotational constant B of 20.956 centimeter inverse. So the characteristic rotational temperature theta r is 1.4387 centimeter Kelvin multiplied by 20.956 centimeter inverse, which gives rise to a temperature of 30.1494 Kelvin, which is very reasonable. Okay, so therefore for a given temperature, say 300 Kelvin, at T equal to 300 Kelvin, okay, T by theta R is equal to 9.9505. Okay, so you have to use the expansion terms now, the related expressions. Okay, so using that, the rotational contribution will be equal to, so the expression will be something like this. You have to use this because it is less than 10. Okay, so you can find out this S by R rotation is equal to T, is the entropy, rotation divided by dt constant V plus ln z rotation So Z rotation, then you can basically use the expansion, and you take the first derivative, which needs to be, that means the correction terms needs to be evaluated. So the correction terms, for example, ZRC will be 1 plus 1/3 theta r by t, da da da. So it is like 1 plus 0.0335 plus 0.0007. The first two terms are sufficient because it drops off quickly. The series drops off quickly. Okay, so RC prime is 1/3 theta r by t plus 2 by 15 theta r by t square, da da da. Again, depending on the situation, you evaluate few of the terms. So 3350 plus 0.00135 plus 0.0000, there are 4 zeros, 4, which is basically 0.03489. So this is the term. Okay, so the rotational Z rotation therefore becomes T by sigma theta r ZRC, which is 9.9505 multiplied by 1.0342, which is like 10.2908. And if we now evaluate T, the derivatives, rotation at constant volume, this is 1 minus the first derivative of the correction term by RC, which is equal to 1 minus, this is 0.03489 divided by 1.0342, which is equal to 0.96626. Okay, so sigma equal to 1 for heteronuclear diatomics. Okay, so the dimensionless entropy now becomes S by R rotation equal to T Z rotation divided by dt at constant V plus ln Z rotation, which is equal to 0.96626 plus ln 10.2908. This gives rise to 3.2976. Okay, so the entropy, finally you get the entropy as 3.2976 into 8.3145 joule per Kelvin mole, which comes out to be 27.418 joule per Kelvin mole. Okay, so this actually tells you roughly the story of the full thing. Okay, so there are more things that one can do for the symmetric and the antisymmetric. Now we go to the final thing, which is the vibrational mode. Now the vibrational energy levels and the degeneracies we already know. So this GV, V plus half omega E, and the degeneracy is equal to 1. So again, if we place the zero of energy at the ground vibrational level within the ground electronic state, okay, so therefore we express the vibrational energy of a harmonic oscillator. If you recall that vibrational energy of a harmonic oscillator is this we have done now countless number of times, so this is what it is. So the vibrational partition function therefore becomes Z vibrational summing over all vibrational levels, E vibrational divided by kT, which is equal to summation V equal to 0 to infinity exponential minus theta V by T. So the characteristic vibrational temperature therefore becomes HV by K, which is equal to H by 2 pi K naught by mu. So this we already know. So theta V is roughly 10,000 to about 6,000 Kelvin for full excitation. So it is very difficult to expand this in a series, but we can use convergent geometric series in these cases. So if you recall convergent geometric series rather than an Euler series, geometric series in this case, which means summation say n equal to 0 to infinity x to the power of n is 1 minus x 1 so long as the mod of x is less than 1. Okay, so here of course we can assume that our x is nothing but exponential minus theta v by t. Okay, because mod x is less than modulus of x is actually less than 1. Okay, so from here we can obtain the vibrational partition function as zv is 1 minus exponential theta v by t. We'll look at it in a little bit more detail in the next lecture. Then we will do the subsequent standard partial derivatives of the partition function with respect to temperature to evaluate the properties. But this is fairly straightforward. We are now well versed with how to go about doing things. Only the zero of energy is particularly important, and that is what you need to protect for doing these kind of calculations. So we'll finish this vibrational part of the partition function and use it. We'll do a sample problem also, and then basically complete the diatomic gas part of this particular course. Thank you.